hello. Hello, hello, hello. Oh. Let's see. Are we connected to YouTube? Okay, YouTube thinks we're connected. Twitch thinks we're connected. Does the chat message get through? Oh. What? Send it. It's going. I don't seem to be able to send a message. Excuse me. Okay, I can send it directly to YouTube. Can I send it directly to Twitch? Apparently I can. Can I send it to both? Yes. Okay, now it works. All right. That was weird. All right, welcome to Code Hangout number 266. Today, I'm going to revisit something I worked on a while ago. And that's on some GPU code I wrote for a research paper I'm co-writing with Professor Neil Calkin and Eliza Gallagher about the algorithmic measure of similarity of Sudoku grids. And today, what I want to do, since I'm starting very late and I probably only have an hour, I want to basically just get the old code up and running again and see where it's at. So I know there's an HTML file, and I'm pretty sure I need to run it with like a little server. So if I do HTTP server, if I just run this here, right? So that would be under localhost 8080. So localhost 80. Gosh darn it. Gosh darn it. All right. And then compsols.html. Okay. So that just runs immediately. Okay. Cool. Now, what does this run? So it runs obviously this bit of test here, start work quad. Okay. It loads one of these three files in. Fetch stalls 100k. So fetch stalls. Where's that? Okay, so that's probably in this JS file that's being loaded somewhere here. Right. Oh yeah, here we go. GPU comp help us load source comp source. Okay, so I'm guessing there's a lot of code that we don't strictly need. All right, so I'm gonna probably want to do, as a first step, I'll probably want to create a version of this that doesn't have the code in it that we don't need, because I remember looking into this and like one of the files was like big. One of the JavaScript files was quite big. Also, wait, we also have matrix comp, and I don't know if that's... Oh, I think this is older. I think this is where I kind of figured it out. This is from March. And then this is from... also from March. My God, it's been over a year. 20th of March. 8th of March, yes. So I think this is kind of where I figured it all out initially. And then this was like the GPU optimized version of it. Right. Okay. So the JavaScript file, so we have load source, we have comp source, we have GPU comp, we have helpers, load source, main RS. What is an RS file doing here? That's Ruby. I think that's something somebody else wrote. Okay. So, and the HTML file is comp source here. So let's get our notepad down bottom. Yeah. Well, Keith, how are you guys doing? Yeah, we're doing all right. I've barely seen Toby because he's been... The in-laws are visiting and they're on the other island, so he's been there with Greta and I've been alone here, slaving away. I did go over to visit, but tomorrow they're all going back home to the UK, so Toby will be back home, hopefully. Yeah, he's not here today, unfortunately. I think he's chilling by the pool right now. Let me see if I've got a pic of him by the pool. Oh, I'll probably have to scroll back. How far do I have to scroll back? Alright, that's a video clip. We're going down the video clip. Alright. I don't have an updated pic of him chilling by the pool, but they do exist. Okay, let's figure out what's going on here. So, we have this piece of code here. So what does these fetch sols commands do? Fetch sols URL, that's probably related. Okay, so this one loads a text file, and that's it. All right, so the random Sudoku grids, for example, let's have a uniform random, so it's an 8 megabyte text file. Okay, so these are just line break relate. So it actually loads this 80 megabyte file every time this page gets opened, which is obviously silly. No, it doesn't load that. Huh. Because I'm also seeing these text files. Solution sets. A. Oh yeah, I just removed the line breaks. Right. I'm trying to remember exactly what order of things were happening here. Compare all. Because obviously we have an image here on the screen that we're seeing. And I also know that I've done a much larger comparison run. So this image... So we have a render canvas where we're doing the operation. We have a 105 by 500 that we load the solutions into. Compare all context, right? Context. Init sols 3. 0, 1, 2, 3. Fetch sols puzzle DB. All right. So fetch sols puzzle DB. Yeah, I'm gonna take a moment here to figure out what's going on. So we have do work here. Start work. Set quads. Slice. Quad. I don't remember what a quad is. Oh, what is a quad? Because I think a lot of this is actually just the user interface to kind of show what's happening. Let's have a quick look into matrix compilation, because maybe this is a little bit more raw. Run test. Did I have a version that was running from the command line here? I don't recall. Do I have a text file here with some notes? Oh, it would be great. Results. No, that's just the result numbers. Okay. P-time batch. Okay. Don't even remember what that was for. We have a zip file. Let's just... Oh, wait. Is that a single file version of the algorithm? Oh, I think this is like... I think this might be a single file version, so it doesn't do like... Ah. Oops. Nope. God darn it. Gosh dang darn it. So if I run compare puzzle... So I think this basically has a compressed version of the puzzle database included into this file. How big is the file? 1.1 megabytes. Or a subset of that. Okay. Okay. So that's probably what I sent to the other guys. All right. Now this, I'm guessing, is not doing the high-speed GPU comparison. That's just doing a basic comparison. Okay, there's my puzzle compression code. Decode. Okay, so most of this is just compression, decompression. And then matrix as I think this might be the JavaScript optimized matrix comparison algorithm here, which is just a naive matrix here, sum squared. All right, okay. Yeah, I'm doing all right. Well, as I'm back to my baseline, which isn't great, but that's where I am. All right, let's see. Okay, so this is the JavaScript algorithm, and then the comp GPU, that's the optimized GPU version that does like a lot more. Okay, so let's have a look at that then. So here it's saying solution source is 0, 1, 2, and we can also start straight from a PNG in it. All right, we're gonna find out where init is. So I'm guessing that's in compsols. Yes. So here we have init. All right, let's have a look at init. Sols source. So because this takes a single set of puzzles, because it compares them all against each other to generate, you know, graphs and stuff like that. And I think this is trying to be super clever, and it basically, it does various things depending. Yeah, so if the source is a string, it assumes it's an image. Else, it assumes it's an array of solutions. So I think we'll probably want to make something that always takes an image, and then we'll have something else that generates the image, right? Because otherwise, we'll just have to generate the image here. Then it sets up the context, and it basically configures the the shader. All right. So far, so good. So that's our init call. Verify solutions. So I think verify solutions checks that everything that's in... Oh my gosh. All right, one sec. If I... Can I do find in folder? Nope. There used to be right click, find files, find in folder. Ah, here we go. All right. Verify sols. Is that shader function? Okay, let's see. Load sols. Let's see what we got in here. Verify sols. So this checks that a encoded puzzle data is correct in the that the PNG file is correct. Okay. All right, that's something that shouldn't be run every time. That's just going to be part of our utility classes and all that sort of thing, right? So, verify solutions, start time, then let's see, compare all. So then we execute compare all on this context. Compare all, set pairs. So this is when we're generating the pairs, I believe. So basically, we'll have a list of puzzles, and we're currently using one of these PNG files, right? 0, 1, 2, 3. No, we're using fetch puzzle solve puzzle db, whatever. Let me see. Puzzle db compressed PNG comp. So that's the smallest one. So what does this one look like? Okay, so that's probably the one that it's currently using here. So that probably has, I don't know. It'll probably tell us how many it has. How many puzzles are in there? We have these. Nope. Why do we have this cached asset stuff here? That doesn't seem right. All right, so that should get us 24,306 solutions and split into 5 sets. 1, 2, 3, 4, 5. So I'm guessing this file is 5,000 tall and 105 pixels wide. It gives us 5 sets, of which the last one is not complete. Okay. And then oh, okay, now I remember, because we're splitting into sets, and then we're doing the comparisons of the puzzles within a set. But then we also have to compare each set to each of the other sets, right? Yeah, okay, and that's what this algorithm does. So this is all the stuff I need to kind of pull apart. I want to separate that out. Okay. I remember this being quite complicated, and it's going to be a bit of a pain in the butt to get my head around this again. So total 2x2 set comparisons are 8. Solution number solves dot length. Total solutions set quads. 1 second. I have a call from a local number. 1 second. Well, an elderly Maltese lady that didn't speak English, so I guess it was a wrong number. That's a new one. Not a scam call, apparently. All right. So let me try to figure out how these pairs come about. So we have 5 sets, right? All right, let's get it to tell us what sets we have. So here we're going to just return, and we're going to output the set quads. So if I reload this now, what is this service worker stuff here? There shouldn't be any service worker, because this has nothing to do with Sudoku pad PWA. Chrome, how to purge cached service worker for localhost. How can I purge that stuff? So can I just go here, go site settings? Oh my god. All right, 1 sec. Don't know what that's going to show us. Oh, I lost what I was dragging. What? I had a tab here. I dragged the tab, and down here. Oh wait, there we go. Found it. All right, so I should be able to just delete. I don't want to delete all local. No, I don't. I don't want to delete all local data, because that's. Although port 8080, yeah, I shouldn't have anything. Just like store. Okay, so 12 application tabs, clear site data. Now we're going to select storage in the sidebar. So I don't actually want to delete that stuff. This is what I want to delete. Okay. Does that do the trick? No. Clear site data. Navigate the relation. Select storage in the sidebar and click clear site data. Where is clear site data? I can't select storage. Ah, wait, here. So can I unregister? Clear site data. Now if I refresh. Okay, I think that got rid of it. All right. So I don't know how we got to verify sols. Because I have the return here. I guess the verify sols happens before that. Alright. So here are the quads it calculates. I don't remember what these quads mean. Alright, let's see. How do we use the quads? Quad. So start work with a quad. So quad I times 21. So that's the width, right? Mark set I plus mark set. That's our 4 markers. Run comparison. Quad. Run comps. All right. Init. Where is run comps? Run test. God, there's so much stuff. Yeah, I needed to do this a long time ago before I forgot what it all was doing. I mean, at least it works, right? But I got to be careful that I don't modify this version that works. I should start with a new one. Helpers. Run test. Alright, where's this function? Run comps. Whoops. Alright, run comparisons, right? That's what it stands for. Execute comparisons. So run comparisons is a wraparound execute that does performance logging. Okay, fair enough. And I think I have that pattern in a couple of places. All right, so sets. So I'm changing from quads to sets. Am I already changing my terminology? Yep. So context, the second argument is quad, which is sets. So execute comparison sets. Sets map. S is null, -1. S, okay. Wait, it doesn't use sets for anything else here. What the heck? Update uniform set start. Sets.map. So if I execute this, so let's say we do the log, and then it was 0001 was the first quad, right? It just does that. So set start in the shader. And now we probably need to start looking at the shaders. Oh dear. I haven't looked at shader code in a while. Let's see, set start. Set start. 0, 1, 2, 3. Okay. And set start is not equals to -1, and set start 1 is not equal to -1. Okay, so it does cater for partial sets. Set start 0 times 500. 5,000. So I'm trying to think if the set start implies horizontality or verticality. Now here I'm hard coding the height of the texture at 5,000. Okay. So this is, I guess I built this for maximum performance, so it has a very strict requirement of what the shape of the data is. And I definitely need the high performance version, but I feel like I also need a more easy to describe version. Or I need a way of running the high performance version in a low performance mode. You know, like how would I use this to compare two puzzles, right? Okay, it didn't take that long to run, right? And I think it was starting from the thingamajigs and generating these images rather than just starting from the encoded PNG data. And I'm guessing for a research paper, it makes more sense to load in the text file and generate the images. It's more that the images, once they are the puzzle data, once they're stored as an image, they're more compact, right? So the text file, so this is the large million puzzle set, and this is 80 megabytes. While the image that contains the same puzzles is only 20 megabytes. This PNG file, right? My god, my brain is immediately just like, oh, you could compress it better as binary data. No, don't do that. Even though it might be true. So I'm trying to remember. They're 23 characters wide. They're 23 characters wide. We have 4 channels, RGBA, right? So 23 times 4. That's 92. And 22 times 4 is 88. So I suspect I have like a blank line there. Let's just confirm that. So if I zoom in here, right? So this is 5 columns of puzzles. So this is one puzzle. Oh, it's 21, not 23. Why did I think 23? So 21 times 5 is 105. So 21 times 4, 84. Yeah, okay. So the last 3 bits are unused. Sorry, the last... So, okay. So we have an... I should take some notes here. So we have... And I need to document all of this as well. So we have 32 bits per pixel. RGBA, right. So we have 32 bits per pixel. So then we have 21 pixels per 81 digits. 81 plus 3 blanks. So we're encoding a digit per pixel. Okay. All right, so that's kind of super wasteful, right? Because technically we only need like 3 digits per pixel. 0, 1, 2, 3, 4, 5, 6, 7, 8, right? So we could make a super compressed version of that, but we'd have to decode it. So this was a lot easier to work with on the thingamajig end, right? But we could technically encode it to oh, I wonder. I think I might have had a problem where I couldn't get the exact bit counts. I think, yes. I think I had a problem where, because of color space conversions, I wouldn't get 100% accurate pixels once I was drawing it onto the canvas. So when I was trying to encode a bit to a bit, basically, or 3 bits per character or something like that, I wasn't getting the exact accurate puzzle data coming through. So I think what I'm doing here, actually, it's not a naive encoding, if I now recall, but we're actually, let's see, split channel, calc comp, digit to bit. So digit to bit, right? Equals bit int bit 1 digit equals bit. Get sol digit. Get solution digit. So we're doing a textile fetch. Yes, so we're basically just stretching it by 9, right? So we're encoding values 0 through 1, or we multiply by 9. So each digit actually has a range of numbers that code for that digit, right? So 0 through whatever, 0 through 23 would be 1, 21 through 40 would be 2, etc., right? So that means now it's robust against color space modifications. Okay, so that's what this was doing. All right. Yeah, because the other thing I would like to do is I'd like to have a version that runs without the browser. And I was looking at that very, very briefly the other day. So if I've node web GPU, so there's something like this. And I think it means I can Drawn as an implementation of web GPU. It includes a node plugin, a sweeper build that plugs on. So I think that lets me execute shaders, right? API for performing operations such as rendering and computation on a graphics processing unit. Normative. Okay, I need to know if this replicates this context, right? Okay, I'm gonna risk talking to Gemini about this, but I have. Oh, let's just go straight to Gemini. I have an highly optimized algorithm implemented as a simple HTML page on some JavaScript and GLSL shader code. Data is loaded in as textures and the shader executes the computation. Output results to another texture. I would like to create a command line tool in Node to do the same without browser. Can I do this with something like Node Web GPU or similar Node libraries? Let's see. You can GPU-driven computation outside the browser using Node.js. However, Node.js will not directly execute GLSL code because Web GPU is a different shader language called WGSL. Oh no. Depending on whether you prefer to keep your GLSL code untouched or rewrite it for modern performance, you have 3 main paths. Keep your current GLSL texture logic easiest. If you do not want to rewrite your GLSL texture on the pipeline, you can create headless WebGL context directly in Node.js. Okay. Pure Node.js hardware accelerated. Headless GL installed as GL provides a native WebGL context without launching a browser. How it works: you replace standard DOM calls with required GL with height. You pass your texture in under to a frame buffer object. Extract the results back to Node. Blah blah blah. Native can occasionally be fitting during npm install depending on the graphics drivers. Yeah. Modernize the web GPU. If you're open to rewriting our web GPUs built specific for non-graphical GPU workloads using native compute shaders. Does web GPU also run in a browser? I'd like to keep the same algorithm and have 2 ways of running it. Let's see. Native modern web browser was designed from the ground up by the If enabled across all major desktop browsers, Chrome, Edge, blah, blah, blah. How to rewrite oats on both environments. Because both Node.js browsers post the exact same API. Couldn't structure your code. Okay. Let's see. How would I convert this code to web GPU? Let's see. And I'm not gonna make this a yell at AI session. I'll tell you that. I'm just curious. Evaluator, likely checking Sudoku grid solutions. It reads 81 digits per solution from an input texture grid, calculates dot product overlaps between pair combinations of solutions, manually packs 16-bit integer metrics into vec4 RGB color channels via bit splitting. In WebGPU, we eliminate all pixel packing, texture sampling hex in UV coordinates instead of rendering a quad across a screen. Pass raw solution digit arrays as storage buffer of 32-bit integers. Provide results directly to an output array, blah blah blah. Display 2D compute grid where work group IDs map to XY directly match solution indices. Is it likely that this thing will actually run? Categorize end results into custom 8-bit split floats to write them into RGBA pixels. Output 30-bit U32 arrays directly to memory. Direct memory indexing and UV offsets arithmetic are replaced with simple array access. Okay. Performance gain. WebGPU skip steps. 100% overhead and fragment rasterization entirely. All right. Now I'm intrigued because maybe for my own ego, I like the shader version, but for the paper, WebGL would probably be better, a WebGL version. So compute shader dot what is it called? WGSL. All right. Where's the scroll bar here? There it is. Jeez, I hate auto hiding scroll bars. It's so stupid. My God, freaking who uses spaces at tabs? And then first it was four spaces, and then here it's 2. That's so stupid. All right. So webgpu.js test.js. All right. So helper from earlier. GPU setup JS. Helper from earlier. Okay. Sure. Oop. All right, I'm actually gonna make a folder here. So we call this web GPU. And then put all these in here. GPU setup. Okay. So it executes GPU setup, run computation. Where does it load in the shader? Or is that in here? I guess we'll install Node Web GPU. Okay, so I do install node dash web. Can I just do this? And npm install node dash GPU. Okay. So execution pipeline. Where is the shader loaded? So the converted out compute shader. Where is the compute shader loaded? Okay, that was atrocious spelling. Data module. Where's this step 4? Jesus Christ. Okay, so this code won't even execute. Can you tell me all the incomplete spots I need to fix? Let's see if it can tell me all the stuff that is broken in this code. Never declared to find blah blah blah. Wait, what does it want? Okay. Let's see if we can put that here in the top. I'd be very impressed if this just works like this. Convert. God damn it, it did it by 4 again. All right. So here are the incomplete spots and hidden runtime errors in the previous code segment that need to fix before it works. Okay, so we have this. It just did this wrong. Okay. Struct uniforms. Oh, I think that's in the shader, right? What did it change? What? Structure must end with a semicolon. It's already ending with a semicolon, all right. Okay, I'm missing async import top level execution guard. If you're running this in Node.js, standard common.js require will crash on a top level of wait. If you're running crash top level wait. The script needs to use ES module type in package to be already wrapped in an async main function execution block. Where is that? Run computation. Okay. So. Okay. I don't know why this is in a separate file. This seems dumb. Can we just put this up here? We just do that. And then this is our execution. Okay. Where is the solutions data? That seems a little bit dumb. Run computation. Wait, what? Run computation. Oh. So none of this actually works. Huh? Yeah, and it doesn't actually care to do, I mean, okay, I said I wasn't gonna yell at AI, but like, it's basically like a junior who doesn't know what they're doing. Like, oh yeah, here it is, it's so easy. Like, no, that's not gonna work. Oh yeah, here it is, so it's so easy. No, that's not gonna work. So it's giving, I mean, it's like 90% there, but like, that it's not finished. It's the code doesn't run, right? Okay, come on. Still, none of this actually works. Can you give me a single file version with two 81-digit strings that it compares, so I can verify your algorithm even works? All right, let's see if that works. All right. Can you not indent by different amounts in the same file? 2 spaces, or preferably just tabs. This is so dumb. Yeah, I don't think it can actually, because I think it converts it somehow by the time it gets to here. Oh, maybe it can. Wait, I delete this. If I copy this, it gets converted. That's so dumb. All right, well, that's so stupid. It does. It actually. I think it actually did the right thing here, but it's the code copy thing that breaks it. All right, so if I just run test.js, I would be very, very surprised if this just works. Yeah, it immediately breaks. But that might just be because of the module thing. Didn't I install Node Web GPU? Does Node Web GPU not exist? npm Node Web GPU. Oh, it's just web GPU. I hope that's not a big complex install. Should have done that. Okay. Wait. Node web GPU doesn't exist? Oh, maybe it does. Node dash web GPU does not exist. That's hilarious. So far, it hasn't run yet. Oh. I renamed the thing. Okay, so that's not right. Workgroup dispatch grid. What? Illustrated. The test script. Did it really just draw this graphic? That's kind of cool. Dispatch 2 for illustrated GPU cores. Oh, okay. No, that's it. It just found this online and claimed. All right, fair enough. Since workers calls dispatch workings one to process a single output element. When you scale this up to 1,000 matrix combinations, you must dispatch threads in parallel across GPU hardware cores. We should use standard thread block size, yada yada. Just count using ceiling division. Creates underlying native threads as across hardware handles. When your nodes version, the script might hang in your terminal after printing, which John's background thread pool remains active. Access king over current process access at the very end of your script. Well, my God. Let's just give it a try. Oh, nope. Let's see what it'll say to these errors. It's 90% there. Back in the 80s, at Sterling University, there was a saying in the computer science that 80% of programs are 80% complete. 80%. Yeah. The first 80% are the easiest. It's the second 80% that'll get you. So here's what those messages mean. Native GPU code actually executes past the web GPU setup phase, so blah blah blah. GPU output, CPU verification. 45632. What does the indicate? It should be a value between 0 and 3. It's like I'm telling it what to do. It read the manual. I didn't read the manual, so it knows how WebGPU works, but it's not a programmer. Its thought processes are so flawed. It's like talking to a university student or graduate who read the book but doesn't think. They just they learned all the syntax and they know how to program, and you can tell them, hey, implement this algorithm. They'll implement the algorithm, but they don't think about it. They don't do things correctly. There is no blank or unmatched. I don't even know what you mean by that. It just scaled by 9 to get to simply operate on digits 1 through 9. Basically ignoring zeros. This should not be needed here, and you should map everything to ranges of 0 through 8. So if I do this and I just paste that and I just save that and I just run it again, whoops, nope, no, and then run it, I get that. If I take this, paste that, and I run this, it still doesn't scale it. Still seems to be wrong. Oh. What? Now that it between CPU and tube outputting for lasted, could you expect 0 to 3 range? Value was passed to speed channel which packed the number into 3 texture channels. That number is just wrong. The math itself should not produce it. Let me get it the draft paper. Oh dear. Wait a second. Ah, no, it's just here. So I can just go in here. Wait, where is it? Where's the PDF file? Do I not have that here? Let me download. I've attached our draft paper so you can perhaps understand the context of the algorithm better. Let's see if it can read the paper. Set of the solution 81 values. You present an unordered set of partition 9 disjoint subsets. To calculate similarity between two grids 9 and B, your algorithm evaluates the total pairwise dot products overlap between their subsets. Mathematical explanation, usually computes the exact formula in calc and then multiplies the results by 64. Does it though? Do I not have shader here? JavaScript shader. Is that under S or under G for GLSL? Shader languages. Here we go. High level shader language. Here we go. What are we looking for? Oh, that was the wrong file. Comp0. Comp0 is just a very basic matrix multiplication. And calc value. Yeah. Why? Where's the 64 coming from? Where is the 64 coming from? Calc comp 0 is a basic matrix multiplication. Where does it get 64 from? That line doesn't exist. The return line is line 62. Looks like this. It seems like it just can't remember it and it's just making it up. Yeah, so it got confused. Yep. We have calcomp 2, we have calcomp 0, and we have calcomp nothing. Where is calcomp 0? I'd like to compare. Yeah, this one went from 1 through 8, I guess. I can't believe it got confused by something that I would expect a human to get confused by. That is kind of hilarious. Poor thing. Hey, look at that. Okay. Well, maybe that's the version I should try to implement. The algorithm is going to be a lot simpler. I'll just have to figure out how to parallelize it. All right. Can you update it for an arbitrary set of grids? Assume they are in a single string variable, line break, 81 digits per line, and I want them to be compared against each other, not against themselves, and not in both directions, of course. Let's see if it can do it without changing too much code, or if it's just gonna... Okay, triangular indexing, for example, is the sort of thing that that I should get my head around. So if I run this now, is that gonna do it? 0, 1, 0, 2, 1, 2. Okay. Does this optimize across many cores? My original code reached around 2 million comparisons per second. It's unoptimized scalar WGSL. It's which we know near 2 million comparisons per second because of massive thread divergence and unrolled loop memory latency. Okay, to reach and suppress 2 million primitives, 3 crucial GPU optimizations. The bottleneck in the naive code. Memory fetch overload. 81 by 81 reads per pair. The inner loop reads Skitzel digit 8,561 times per single digit grid pair. The GPU memory control gets throttled, fetching individual scalar I32 values. Dynamic working size for small n workgroups leaves most GPU units idle. For small n, for massive n, it doesn't take advantage of GPU shader memory. Branch divergent. If dig equals bit inside nested loop creates branch divergent across SIMD execution waves, warps wavefronts. Bit pack the 81 digits. 9 times UN 32-bit masks. 9 UN 32-bit masks. Instead of storing 81 raw digit integers per grid, encode each grid as 9 32-bit or 128 bits. Bit mask for each mask. Presents an 81 cell position containing digit K. Oh, wait, what? Instead of storing 81 raw digit integers per grid, encode each grid as 9 32-bit bit masks. Ah. Ah. That's U in 32. So wait, U in 32. That's not 81 bits though. Wait, storing inner. I was gonna say, or 128 bits. Wait. Where each mask represents the 81 cell position containing digit K. Evaluating digit overlap between grids A and B simplifies to bitwise AND, followed by population count. What the fuck? This does not create a matrix multiplication. What are you? It's trying to create a new algorithm. No, slow down. You're missing the point of the paper. By converting the problem to a matrix multiplication, it becomes completely robust to digit swaps and various identity transforms of the Sudoku grids. Variables. I am implementing this algorithm to provide data for the paper. If we change the algorithm, it's useless. What the frick are you doing? It's like it completely misunderstood what the hell we're doing right now. And we're not just checking for identical grids, but measure similarity. On a smooth spectrum. Yeah. Of course, I need something that produces identical output to my WebGL code, so the results are comparable. So I don't want to change the algorithm. And the speed wasn't due to matrix performance, matrix multiplication performance on the GPU, since the matrices are too large, by 9 each, so I implemented it myself, but it is fast due to massive parallelism, as it basically executes one comparison per pixel in the shader. Parallelism. Multiplication. My god, my typing. I don't think it quite understood what my original algorithm was doing. But it makes total sense. To ensure the results are run according to existing research data, the web GPU must run your exact original GLSL code without altering a single mathematical operation or outputs scaling step. Outputs end by empirical comparison by mapping each pair to individual pixel thread running the exact call routine parallel across the GPU cores. It's doing the times 864 again. Jesus Christ. Okay, we do have output stored somewhere here. I'm pretty sure. I forget what the sol sets are. Well, okay. I can probably use this and figure that out, and maybe I need to learn a little bit about WebGPU and how fast optimally I can implement it, and I might want to reuse some of my code to split it into those quads and sets. It's getting late. I started late, so it's going to be a bit of a shorter stream, and I fell into the trap again of listening to Gemini when I should be just looking at the code myself. But to be fair, it helped me also kind of to remember, you know, ironically, misunderstanding my code taught me or reminded me of what my code was actually doing. So hopefully I can maybe go back. I feel like I almost should start from scratch and kind of implement it slowly, step by step. Because right now this code kind of, I think it sort of is super flexible. It does all sorts of things. And and I might want to reduce the number of different things it accepts and make a simpler version of it. So maybe get rid of the PNG handling. Just do, because I looked at it and the code that converts the source to canvas code is not like super complex if I look at it here. Or maybe it is. No, doesn't look too bad. So maybe I can just remove it. Maybe get rid of all the check code. Yeah, because it's really just one line here, right? And that's just one line basically. And then that's just one line, right? So I can probably turn that into a very small, simple function. Yeah, let's do that, for example, right? Let's create a simple source to canvas version. So if I take source to canvas, right? Put that here. And then source to canvas needs write sol ID data, whatever, right? Which is this one. Right. And then this one needs dig to byte. Right. So that's in principle what that function does, I think. Right. So we have create source canvas, so there's a couple other ones. So we have create source canvas. It's like it's wasting space here. So we have create source canvas, will read frequently true, write sol canvas. Right. I think that's pretty much it. So now if we get rid of all the logging, right, and then create source canvas, we put that here. Right. So we'll just say canvas is this. Width and height is that. Width. So if I say const width equals this, height equals that. Can opts is undefined. Will read frequently is ctx opts. Okay, so that's here. Just do this. And we don't need that. Do a quick fill of that. Like that. Right. So now we don't need that anymore. Width, height. I'll just do that. Don't need that. All right. So then we have this. And then we get to there. So that so for each solution here, we'll do this with iData. It's tickling my nose and I don't know what it is. Anyway, I think we can do this here. Right. Sols to XY. So that's what comes in. So we have 8 iData, sure, out of which we pull data, sure. Then we have sol, which is sols s. So we'll do sol equals sols s. That's our sol. And then sol to x, y, id to s. Okay, sol to x, y. So we need a function called sol to x, y. I just saw it here. Okay. So we have a function called sol to x, y. Now, sol to x, y operates on what exactly? So sol to x, y returns an array, which we split into the two arguments at the end of right sol I data, which is x and y. Okay, so this would be x and this would be y. So const x equals and y equals that. Right. Now, we have I data. We have width and height here, w and h, width, and then we can just do height here, which I don't know if they're the same as these up here. I think they might be the same. I think they might be the same. So we'll probably want to do height here, height here, and width, w, width. And then we can get rid of that. Right. And then we have x and y coming out of these. Go into this function, which I used here. Y times width, x times blah, blah, blah. Right. And then dig to byte, finally, which is this little thing here. So sol d is that, and that's our dig to byte function. Boom. 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 Right? And that should be a single function version of that, which is barely bigger than the original sols to canvas. So if I do this, and then we'll go back to here and change that to sols canvas 2, and then init from sols from array. So if we now say 0, 1, 2, 3, if I now go back to here and then refresh, all right. Let's make sure it's actually executing this. Looks like it. Cool. So this is, for example, you know, a way of making things simpler. And canvas to sols, I don't know if that's used. It's also not very complex, right? Can we simplify this further? Do we need the fill rect to 0? I think so. We do a fill rect here. Height equals set size. Height, width, height. All right, yeah, okay. Now set size is the height. Oh, okay. So we can probably just pass that in as an argument. like that. Or do that. We could... Yeah, I don't think preloading it to 0 actually makes a difference, right? Because we are... x times 4 plus d times 4 plus d. Yeah, we don't technically have to preload it to black, but I don't know what it will then contain in those couple extra pixels that we're not using. Yeah, and it'll fail on the verification, yada yada. Plus D, 21. So 21 times 4 is 84. So if I do 80, 81, D is if I say 4D, so if I start D here, let D equals 0, then we'll do while D is smaller than 81, D plus plus. While D is smaller than 84, we'll just say this is static, right? So we probably want to do IDX equals this. Right, and then this is IDX, and then this is IDX, x equals 0. So if I do this, we still get failures. If I do this, we still get failures. Is it because we're not filling in these? So if I fill in these, I don't get these verification failures. I do get the verification failures. Wait, what? Huh? Wait a second. Why? Shouldn't that simply set everything to 0? It doesn't set the alphas to 0. It sets the alphas to 1, right? But I am also using the alpha channel here, which is why they look a bit funky. This is really annoying. I'm trying to think. So doing this, I think our RGBA is 000255, I think. Which means if if let's say 83 modulus 4, so 0 modulus 4 RGBA. So if D modulus 4 equals 3, then 255 L0. If I do this, and if I do it for like, let D equals 0. If I do this, let D equals 0. If I do 21 times 4, 84. 84. 84. If I do this, IDX should always be aligned on a pixel. Yes. Let me introspect. What does it look like? Zero 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 255 000 255. Now, if I don't do this, what does it look like? Probably the same, right? Ah, so all zeros, right? Now, if I do this, do we get 000 255 or do we get something different? 000 255 000 255. But I suspect it doesn't happen at the very end when we don't actually have puzzle data. Yeah. And our verification algorithm kind of wants that. What if I just do if I just say for I smaller than data.length, I plus plus, I that, and then we do that. Right, because now, even at the very end, it is pretending to be filled in with blank pixels. All right, so we can get rid of these. Why am I doing this? Probably to reduce my dependency on DOM stuff. I mean, I do need the image data stuff. Like, is this faster than this? I don't know. But why not? XY IDX. XY IDX. S divided by height times 21. S modulus height. No, S. Yeah, S modulus height is our Y. Height being the 5,000. Okay, the set size basically. Sol D. Sol's SD. Math round times 255 divided by 9. Okay. So for example, I could show it this, and this is how let me see what it says. By the way, this is algorithm that converts digit lists into the textures the WebGL version uses. Let's see if it can understand that. We're stored in decoding WebGL. There's no pixel encoded word. Each digit string was a value of 1 through 9. Each digit was mapped to an 8-bit RGBA pixel channel. Math round digit times 299. Inside UGSI fragment shade, reading the texture channel returned a normalized float 0 0 1. The GSI showed reverse the formula to retrieve the original integer 1 through 9. Yes. Feeding WebGPU. In WebGPU, creating canvases to the context and uploading image texture was necessary to pass data, blah blah blah. You write the digits 1 through 9. Yeah. So, this was very efficient. In my largest test, I encoded coded 1 million grids into a 29 MB PNG file. The output was a 5000 by 5000 pixel texture. Here. Wait. Am I not executing the... I am not. So let's run it. Boom, 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 boom. Pixel texture. Oops. Texture for each set of 5000 puzzles. Compare 5000 sets of grids compared against themselves. I then efficiently calculated all needed comparisons between all sets of 5000, which got me the 2 million comparisons per second. Well, this is required as 1 million puzzles compared against each other requires... How many? Does it tell me? I think it used that formula at the beginning, right? Where's my scroll bar? Why don't I get a scroll bar? Where's the scroll bar? I want to scroll. I don't see a scroll bar. I hate invisible scroll bars. Oh, there it is. Jesus Christ. Why the invisible scroll bar? Jeez. I don't understand it. It was, I think, in some of the earliest thingamajigs. I'm guessing it's squared half, roughly. -1. So I'm guessing it's what? It's 1 mil. Why google.tk? What is TK even? Why Google? Why maps? Hell. Anyway, 1 million times 1 million minus 1? No. X to y times that minus 1 over 2? Minus 1. 0.5 times this? I guess. Requires total comparisons. If I didn't get the math wrong here. Full screen quads to render targets. 6 minutes per work group, directly mapping to your 5000 by 5000 set comparison blocks. I don't understand how these 16 by 16 thread work groups map. The script processes large sets and chunks of 5000 puzzles. Running your exact comp algorithm. 1 million puzzles. With 1 million puzzles split into 200 sets of 5000. Auto execution loop, blah, blah, blah. Okay. I'm gonna call it here now. It's getting late. I gotta figure out what I'm gonna do for food. Yeah, I don't that invisible scroll bar. I think I also have some burn-in on my monitor, which is a bit annoying. I'm shopping around for a new monitor. Maybe when memory and storage is expensive, maybe I can get. Whoa, maybe I can get a monitor without paying some stupid AI tax. At least AIs don't need monitors, I think. Anywho, I didn't do everything I needed to do, but I got started. I got myself refamiliarized a little bit. We wrote a tiny little bit of code just so some of the rust shakes off, perhaps. Yeah, thanks for hanging out, Keith. Appreciate you stopping by. And catch you guys in the next one, or on the Discord server, or in my emails. Take care. Have a good rest of your